All right, guys, let's give it 2 more minutes. You. All right, 1 more minute. All right, let's go ahead and wrap them up if you haven't done so already and pass them in. Anybody else? Want to come up there? All right, guys. So let's go ahead and pick up where we left off. All right, so I put a video up for Wednesday, right? Did y'all have any questions you wanted to ask me regarding information from that video? We went over with practice problem with allylic halogenation, but as far as new stuff, I talked about radical addition of HBr to double bond, and then I did a couple of synthesis problems. All right. Any questions on those? What's the purpose of doing radical bromination of HBr to a double bond? We've already learned how to add HBr to a double bond, right? We did that back in the alkenes chapter. Yeah. Double checking to make sure you guys actually watched the video. All right. Yeah. This is a Markovnikov edition, and this is the way that we did it back in chapter whatever. What was it? Chapter 10, maybe? Yeah. But we saw that if we did this through a radical process, right, and so whenever we do this, we have to have HBr, just like we did before. But we also have to have the presence of something called a peroxide, which we see here, and then either light or heat. And that allows us to have the anti-Markovnikov. And that's real convenient, right? Because sometimes in a synthetic process where you have to go through a point where maybe you have a halogen on sort of an inconvenient spot, right? a place that's difficult to get it through traditional Markovnikov addition. Well, this is a great way to remedy that. Okay? Let's do one. Let's go through a mechanism one just to make sure you got it. Okay, so all right, let's say we're adding UV light just to be different. Okay. All right, so let's go back over the mechanism of this. All right. Again, hopefully you watched the video. Just like any other radical process, you're going to have initiation, propagation, and termination. All right. Now, what's going to happen in initiation? Yeah, initiation is always where you make radicals, right? And you notice that we have a peroxide here. Peroxides are especially unstable. And so, whenever you add your energy source, it's really easy for them to split up into radicals. So you get two of them. All right. Now, this is kind of unique because of the mechanisms that you've learned so far. Initiation has only had one step, right? For this particular type of reaction, there's actually two parts of initiation. The first part is making this, and then one of these interacts with not that. Interacts with HBr. Yeah, sorry, go, what was it?
No, you're saying.
Yeah, HBr. How does it interact with HBr? What does it do?
The BR turns into a radical.
Yeah, it flux off an H radical. And it makes an alcohol. Now, the alcohol is not important. It's just a byproduct, just a waste product. But more importantly, you make your BR radical. All right? That's basically the purpose of any of these initiation steps, is to make a BR radical, or in the case of chlorination, a Cl radical. All right? Once you make your BR radical, then you can proceed with propagation. Can I erase this last one? All right, so once you get to propagation, that's where your hydrocarbon reacts with the BR radical. Now, previously, we've seen that we end up with, some sort of situation where your hydrocarbon loses an H radical, right? That's going to be a little bit different here. What happens in this case? What does that BR radical do? Splits the double bond. All right. And it's going to add to one of the carbons. Which carbon does it add to? Well, there's a couple of possibilities. You could have added to the carbon on the right, and in that case, you would leave a radical on this carbon, or you could have attached yourself to the other carbon and left a radical over here. Does one of them preferentially occur? Do they both occur? What do you think? One on the left, why? Why the one on the left? Yeah, look at the type of radical they've made. This is a tertiary radical, right? This is a secondary radical. Which one's better? Tertiary. So this is the case where we specifically go through just one radical. All right? So you make that one. Then the second step of propagation is abstraction of an H from HBr. Right, you get a Br radical, which continues the propagation, and you end up with that. This happens to be racemic mix here. Bless you. And again, you can see this is an anti-Markovnikov addition. If we're doing this ionically, right, where you add H plus and then you add Br minus, if that was the case, the H plus would have gone here and the Br would have gone here. So whether it's a radical or ionic mechanism, that's really important. It plays a big role in where your components end up being. Okay? Does that make sense? That jive with what you went over in the video? Because I'm sure you all watched it, right? Some of you are like, nah, yeah. Some of you are like looking down at the desk. If you haven't watched it yet, be sure to watch it. All right. Also in the video, I did a couple of practice synthesis problems. I'm going to do a couple more before we hit the last topic in this chapter. All right. All right, so I'm going to just pick a couple out from the book. I had them pulled up. Let's see. There we go. All right, let's try this one. All right, we're gonna, let's see if my blue marker's any better. Yeah, that's fine. All right, let's start off with this one. This is ethylene or ethyne. All right, we're gonna use ethyne and then any other reagents that we need in order to make 1-bromobutane. All right, let's talk through this one. All right, take a look at what you got. Take a look at what you want to have. Preliminary observations. What are any preliminary observations you might have just from looking at this? Yeah, you're going to be adding carbons. So if you're adding carbons, what do you think you're probably going to end up doing? NH2 minus, we're making acetylide. Yep. And we want to extend that carbon chain. How do we do it? Alkyl halide. How many carbons do you want? 2. All right. Your wish is my command. And boom, wow. We're already on our way, right? So yeah, you can definitely see that you need to extend the carbon chain. Acetylide is the way to do that at the moment. And you can definitely get a 4-carbon unit that still has reactive components over here, right? Now you just got to figure out how to get from the alkyne to the alkyl halide. And I'll tell you, you can do this in 2 steps. This is also the more difficult part. What's that? H2 and Lindlar? Let's see what H2 and Lindlar would do. You guys tell me, what would H2 and Lindlar accomplish? Yeah, H2 and Lindlar is a way to go from an alkyne to an alkene. Usually it's specific for cis alkenes, but since we don't have cis trans here, it doesn't matter. We could have also used two NH3, two NAs and two NH3s. That would have worked the same in this case. But yeah, I think this would be an excellent step. Yeah, that reaction we just looked at. You're looking to do an anti-Markovnikov addition of HBr to a double bond. Boom, that gives you the product. You guys are on top of things today with regard to synthesis. Dare I say, is synthesis getting easy for you? No? Okay. Just check. All right. Do y'all understand how we got through that process? Does that make sense? Are there any questions? All right. Let's try one more. And then we'll move on through stuff. Okay, I had a good one picked out. Let's see if I can remember what it is. Ah, yes. This one looks scary. So you start off with cyclopentane. And you make this. And you're like, holy crap. That sucks. It's very doable. You can do this one in 1, 2, 3, 4, 5 steps, I believe. All right. Let's take it one by one. All right. Again, look at what you have and what you can do with it. I think it's safe to say we're not adding any carbons here, right? So we're not going to be dealing with the sunlight or anything. Look at what you're starting off with. You're starting off with an alkane, right? Think through the year. How many different reactions of alkanes have you guys learned? You have learned, I can tell you, you've learned 2. One of them was way back in chapter 4. We learned that you can combust alkanes, so you can burn them to make carbon dioxide and water. Do you think that'll be useful here? No. There's only one really useful reactions of alkanes that you've learned. What is it? It's from this chapter. What can you do to an alkane besides burn it? You could do a halogenation, yeah, such as a bromination, right? So if that's the only thing you can do, I would suggest we, probably do it. Okay, so if we want to do bromination of an alkane, we could use Br2, and either UV light or heat, and that does a monobromination. Now, no matter where you go, it produces the same product here, so it doesn't matter where I put Br. I'll just stick it right there. But that gets us off to a good start, all right? All right. Where else would you might want to go with this? I could see working through it forwards. I could see sort of skipping around and working a backward step here and there. I want to see what you guys think. How would you approach this one? NH2 minus? Here? Yeah. What would NH2 minus give you? Okay. I'm going to suggest a different base. NH2 minus would work and give you an alkene. It's also a good nucleophile, though it also give you a mixture of like an amine product. But yeah, you have the right idea. You want to do an elimination with a strong base. This is chapter 8 stuff. And yes, that would absolutely give you an alkene. Very good. So if you're looking at this now, you're thinking a couple of things, hopefully. Number one, you're saying, well, these two carbons from the alkene are going to get turned into an epoxide somehow. And also, I'm putting something in a very specific position. What position is this called? The allylic position, right? So, with those little tidbits of information, how do you think you might want to proceed here?
Yeah, MCPDA to make the epoxide.
You could, and if you added MCPDA, oops, that would definitely make the epoxide. However, I'll tell you, you don't want to do this yet. Reason being, whenever an alkene is here, you have a very easy, convenient way of putting something at an allyl position. With an epoxide there, you don't. So this is where kind of the order of the steps is important. We are going to do that, just not yet. Let's go ahead and put something at the allyl position. Here, what's an easy way to do that? ER2 and heat would put something there, but unfortunately, you'd also get a competing reaction. An addition where the BRs would go here and here. There's a reagent you want to use instead of BR2. NBS. Yeah. You have NBS and heat. That will give you an allylic bromination. Now we're in good shape. We know we have a group we can make epoxide out of, and we have something going on at the allyl position. All right, how can we replace that BR with an OH? This is like the simplest step. What's that? H2O would work, yeah. That would give an SN1 reaction. Probably better to do it in AOH. So I'm going to write that. But H2O would work. And now, I would save the MCPBA for the last step to make the epoxide. Here's a question. If I added NaOH to make this, why do it here and not after I make the epoxide? Yeah, if I had made the epoxide first, this could have broken apart the epoxide. So this is a pretty good one that shows you, how specific the order has to be sometimes. Okay. Again, you guys did a good job working through that collectively. Don't you wish I would just let the whole class work together on, synthesis? Yeah, sad. Can't do it. The MCAT, they don't let you do it, so I can't do it. All right. Are there any questions on how we got these? Does that make sense? All right. There's plenty of good practice synthesis problems in this chapter, so work through them. If you have any problems, let me know. All right. There's one more topic to discuss in this chapter, and it's a little bit different because it doesn't necessarily involve halogens. All right, it involves polymers. It's called free radical polymerization. Guess what? This is what I did my dissertation on. This is what most of my current research is based on. So I know a bit about it. I could sit here and talk forever on it, but I'm going to keep it restricted, hopefully, to what you guys need to know. All right. First of all, let me ask you this. What is a polymer? What's that? I heard somebody say something.
It's
Big, long molecular chains, yeah. So you guys, you see it, you guys might see it like a complicated structure and think, okay, that's a big molecule. That's not truly a big molecule. Polymers are big molecules. They're chains of units that have molecular weights in the tens of thousands, hundreds of thousands, even greater, right? So literally they're like links, individual links that are composed, or excuse me, chains that are composed of individual links. These individual links have a name. You guys know what that is? Monomer, right, they're monomers, okay? So there's lots of different ways to make these links come together. One of them is through free radical processes, okay? And a lot of the common materials that you guys use in everyday life are actually made through free radical polymerization, okay? Y'all ever heard of polyethylene? Yeah, probably heard of that. Any examples of polyethylene that you know of in everyday life materials? There's actually several different types, and they can have several different types of appearances based on not only the specific chemical technique that's used to make them, but also how they're processed, sort of the engineering behind it. Polyethylene, amongst other things, is used to make those little flimsy Walmart plastic bags that you carry your stuff out in. It can be used to make bottles, like sort of milk bottles, juice bottles, that type of thing. It can also be used to make very, very strong bulletproof vests. Kind of crazy to think about, right? Walmart bags, bulletproof vests. Hey, they can be used for it. Now, they're processed a whole lot differently in each case, right? How about polyvinyl chloride, or PVC? You heard of that one before? What's PVC used in? Pipes, yeah, plastic pipes, right? Teflon, probably heard of, right? Non-stick cookware. There's tons and tons and tons of them. I could talk forever. Again, this is a basic introduction. So let me show you how free radical polymerization works, okay? So typically what you do is you have a monomer, and I'm going to use the simplest one here. This is just ethene, common name ethylene. That's where the term polyethylene comes from. They actually use the common name instead of the IU. All right, so you can have this. All right, typically what you have is you have something called an initiator. I'll write that down sort of here in the corner. An initiator is exactly what it sounds like. It's something that sort of kicks off the reaction. This ethylene is not going to polymerize itself, right? It's got to have a reactive radical present to sort of jumpstart things. That's where the initiator comes in, right? You add an initiator in the presence of heat or light, and it produces polyethylene. And here's the way we represent polyethylene. Now, if this thing's like 100,000 AUs, you really think I'm going to sit here and write, every C and H and all that? That would be insane. So what we do is we write something called a repeat unit. Basically, this means you have this CH2 bonded to another CH2, and this little unit repeats however many times. So that N could be 1,000, it could be 10,000, it could be 100,000, just depending on how long we made the chains. Okay. All right. So let's take a look at how the mechanism of this actually works. Just like any other radical mechanism, it's got three phases. You have initiation, propagation, and termination. All right, so let's look at initiation. Initiation is going to be similar to what we learned about most recently, where we did the anti-Markovnikov addition of HBr, right? Initiation is going to have two steps in this case, right? First step, well, we got to make the radicals, right? So just like last time, the very first part of this involves making radicals from your initiator, your peroxide. All right, so we can have our energy source, boom, boom, boom. It breaks that OO single bond, and you end up with two initiator radicals. All right. Once you make those initiator radicals, one of them can interact with a monomer unit. Okay. Now, taking a look at this, just guess, what do you think is going to happen in the mechanism? We haven't gone over this, but I think you guys can probably figure it out. What's that? It's actually not going to take an H. It's going to do something else. Think about what happened with the last reaction mechanism. It's going to break that pi bond, yeah. It's going to break the pi bond. One of these electrons will bond with your OR radical, and the other one will form a carbon radical. So you make that. Okay. So initiation with polymerization, initiation and free radical polymerization involves, number one, making initiator radicals, and number two, making the initial carbon radical. Okay. So far, so good. All right. All right, then let's look at propagation. All right. So propagation got our carbon radical. Guess what? You're going to encounter another monomer unit. What do you think is going to happen? Same thing, yeah. This bond breaks. These two carbons become linked up, and you form another carbon radical. So now instead of having a 2-carbon unit, you have a 4-carbon unit, and you still have a living radical. And this keeps going on, and going on, and going on, et cetera, et cetera, et cetera. And it keeps going until you have enough terminations to kill any of the radical species. And again, there's lots of different types of combinations of radicals we can get. I'm not going to go through all of them, but suffice it to say, if you have 2 radicals, they combine, make a dead chain, is what we call it. Don't produce any living radicals, that is a termination. So, when all is said and done, you have your polyethylene. Okay. Does that make sense? And yeah, this is the simplest one. You can have other stuff sort of hanging off as well. You know, a couple of the other ones I mentioned. I mentioned, what did I say, PVC, polyvinyl chloride. PVC is made from this monomer. A common name for this monomer is vinyl chloride. That's where the polyvinyl chloride comes in. When it's polymerized, It looks similar to ethylene, polyethylene, except it's got an extra Cl hanging off of it. This molecule is called tetrafluoroethylene. It's got 4 fluorines on it. When it polymerizes. Those F's are still there. Within the repeatant. This is Teflon. And don't be fooled, not every monomer we use is 2 carbons. These are just some of the simpler examples that we're using for the moment. You can have, of course, bigger monomer units, but the process, the mechanism, and the way you go about this is the same, no matter what your monomer is. Okay. Any questions? All right. That's the end of the radicals chapter, whether it's 13 or 15, depending on the edition of the book you have. This is a fairly long chapter. The next, let's see, chapter 16 is not as long, and then chapter 17 is actually pretty short. So what we're going to do is we're going to hit the ground running with chapter, in my edition anyways, chapter 16, and maybe a different chapter in yours. It's entitled Conjugation, Resonance, and Dienes, I think is the name of it. So we will hit that on Friday, right? I will, before lab, I will put up a handout for you guys on Moodle that you can use as a reference as we go through. All right? That's all I got. See you later. Oh, just a special note as well, in case you didn't get the message, Alex is not going to be here tonight for supplemental instruction. She's off on a function of some sort. So.
I sent an email before class, and I guess.
Oh, no. Okay.
So no, I haven't. There another time we just text with him.
Yeah, yeah. Yeah, no, thanks for letting me know. Yeah, absolutely. If you want to do it like, we'll probably have some bedtime during lab if you want to do it then. If that's okay.
Yeah, that's fine.
Okay.
That works.
Cool.
Thank you.
Yep.
Thank you. Yeah, you look like legit dead, Lisa. When I say dead, I mean dead.
Oh. Uh-huh.